Right guys, today we're going to be looking at Pythagoras Theorem. You probably remember it, we use it all the time. Given any right angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. That is a squared plus b squared equals c squared. Okay. What we're going to do today is run through 4 proofs of the theorem, getting progressively more complicated as we go, but nothing too crazy, so don't worry. Okay, so proof 1, we're going to look at a square with length a plus b, and we're going to draw within it 4 versions of our triangle. So this is C and C and a plus b. And what we're going to do is we're going to draw the same square again, but we're going to move the triangles around. We're going to bring this one down next to this one up to the corner, and this one across. Okay, like this. Which way around? That way. So now we have this length is B and B and A and A. So we have this area here. The area of the square, the overall square, is unchanged. The area of the triangles is unchanged because translations don't affect area. So therefore, this remaining space here, which is c squared here, must be equal to this space plus this space, which is a squared plus b squared. Okay, so there we go. Nice simple proof. Okay, proof 2. We use the same square, but this time we notice that the entire square has area a plus b squared, because the length of the side is a plus b. And we can multiply this out to give us a squared plus 2ab plus b squared. Okay, but we can also notice that the area of the square is equal to the area of this internal square plus the area of the 4 triangles. Now the area of a triangle is half the base times height. The base is A, the height is B, so it's 4 times, because there's 4 triangles, half A, B. Okay, now we can just tidy it up a little bit. 4 times half is 2, and then you can see we can cancel 2ab from both sides here to be left with a squared plus b squared equals c squared. Okay. Okay, proof number 3. Again, nothing too crazy. We're going to draw a square. This time the square has length and height c. And we're going to draw our triangles inside, 4 triangles again. We're going to draw them a bit differently. There you are. Now this length here is b. This length here is a. Therefore this length here is a minus b. Okay, it's the full length, take away this bit, a minus b. And believe it or not, this is a square in the middle, not drawn very well. So each of those is a minus b. So now we're going to use the same technique we used last time. The area of the square is c squared, but that's equal to 4 times the area of the triangle. So again, that was 4 times half ab. Now plus the area of this little internal square, so that's a minus b, a side length, squared. That's equal to, we have again 2ab plus, and then if you remember how to multiply out brackets, a squared minus 2ab plus b squared. And then you can see here that cancels with that, and again we're left with c squared equals a squared plus b squared. Proof number 4. We're going to not draw a big square this time. We're going to start with a triangle like this with the right angle on top, and we're going to draw squares on each of the sides. Okay, what we're going to do then is drop a perpendicular down from this point down to the bottom. And we're going to construct a couple of triangles inside. you'll see where we're going in a sec. We're going to make a triangle here. And we're going to make this another triangle here. Okay. We're going to call this distance x and this distance y. This is C. All these sides are C. All these sides are A. And all these sides are B. Okay. Now let's look at these two triangles that I've constructed. You can see that they both have one side length C, this one here, and this one here. And next to it they have a side with length B, here and here. And the angle between them, well, in this triangle it's this angle plus a right angle. And then the angle for this triangle is this angle plus another right angle. So they're the same angle. So if you've got a side, angle, side, then they're the same triangle, similar triangles. Okay? So we know they have the same area. Now what I want to do is look at this trapezium shape here. I'll draw it again up here, look. So we've got a square with B here and a triangle there. And then we've got this triangle within it like this. I'll draw it in green again. So the area of that triangle is half base times height. Any triangle is half base times height. It's got base B, height B, therefore its area is half B squared. Okay, because this square was B. Now I'm using the fact that two right angles make a straight line as well there, so they're parallel lines, so we know this height here is the same as this height here. Okay. But also we know from exactly the same logic, let's look at this trapezium here. I've drawn that a bit out of proportion, more like this, isn't it? And then there's our little triangle. So we know that, what did we say? This is x, and this distance here is c. So therefore we know the area of the small triangle is half xc. But we know it's similar to this triangle, so therefore it's equal to half b squared. Therefore xc is equal to b squared, which means this area here is b squared. Alright, and we can use the same argument on the other side. Okay, we draw two triangles, one down here like this, and then one across like this. So we can use the same arguments to prove that these triangles are similar. There's the same angle plus 90. They share a side C of length C and a side of length B, this one and this one. So therefore, using this exactly the same, YC equals half A squared. Therefore YC, the area of this, is A squared. But the area of this whole square here is C squared because we defined it as such with length C here. Therefore A squared plus B squared equals C squared. And we're done. So anyway, that's it for today. Hope you enjoyed it, and I'll see you next time.